Hey guys, this is John. In today's video, we'll be solving the Laplace equation inside a cylinder, but this time, the boundary conditions on the top and bottom are going to be homogeneous, whereas the boundary condition on the lateral surface is going to be non-homogeneous. These sort of boundary conditions will give rise to what we call the modified Bessel functions, and we're going to discuss these in detail and try to understand what's happening. The problem that we have here is more of a difficult-sided problem in terms of these Laplace on a cylinder problems, and I would definitely advise following along closely and making sure you understand what I'm doing. Alright, so let's start off by reading the problem. So we're told to solve Laplace's equation inside a semicircular cylinder subject to these interesting boundary conditions. So we're told at the bottom we're equal to 0, at the top we're equal to 0, and then we're told that this cylinder is basically half a circle, so a semicircle, and we're told the boundary conditions on those sides, and then we're told the lateral boundary condition. So I know I've been throwing a lot of words here, but let's draw the shape. So 0, step 0, draw the shape. Okay, so cylinder, good old cylinder. Oh wait, this is a semi-cylinder, oops. Let's draw the semi-cylinder in this fashion so that we can see the sides. That's, yeah, okay. We're told that at the top, we have a derivative boundary condition. R theta h is equal to 0. At the bottom, u r theta 0 is equal to 0. And then on the lateral side, so the radius of this cylinder is a. U a theta z is equal to beta theta z. Let's call this specific angle right here the 0 angle, and let's call this pi, right? So that this side of the circle, the cylinder, so for u r theta z, oh, that should be 0, sorry. Degrees angle 0 basically is equal to 0, and the opposite side is u r theta z is equal to 0. Okay. So now step 1 is to separate variables. Unfortunately, we're not given all the Laplacian, so I guess we'll just go about and do all the steps out. So we know that Laplacian u is equal to 0. In polar coordinates, the Laplacian is equal to r ddr r du dr plus 1 over r squared d squared u d theta squared plus d squared u d z squared is equal to 0. So what we're going to do is we're going to define u r theta z to be equal to the product of, let's call this phi of r theta first, and separate out the z dependence initially. So what we should get is, on the left-hand side of the equation, we should get 1 over phi times d squared polar Laplacian, this is sort of my notation here to save space, is equal to negative 1 over h d squared h dz squared. So all I did was I plugged in our separation variables. Okay. So now this is where things get a little bit interesting. So we know that the top and bottom here. So in Z, we have homogeneous species. And therefore, we want oscillatory solutions. And in order for that to happen, right, just by quickly looking at this, we need to set our separation constant to be some number so that we can introduce imaginaries into our solution. However, the issue that arises is that if we set our lambdas equal to positive here, the left-hand side of the equation will not be satisfied. So what we need to do is we actually need to set this separation constant as negative here in order to satisfy the left-hand side of the equation, but the intrinsic value of the separation constant is a negative number. Okay, I'm going to repeat this. All right, so we introduce this negative sign here. We introduce negative here. But we have to force the value of lambda to be negative. Okay? And the reason why we do this is because if this negative is not here, we cannot satisfy this left-hand side of the equation. And in addition, if that negative is not there, then the lambdas do not satisfy the boundary condition on the edge of the cylinder. So I'm going to ask that you guys take my word for this for now until I explicitly show the reasoning why we choose to do this. Okay? This is going to be very strange and out of the blue, but once I show you guys the explicit reasons in the future few minutes, then everything should make sense. So let's continue solving for the left-hand side of this differential equation. Let's continue separating variables. So we're going to have this negative phi times lambda. Okay. We know that lambda is r theta, so let's continue separating to f of r times g of theta. And we've seen this separation many times before, so this can be 1 over f times r dr df dr is equal to negative 1 over d squared g d theta squared. Now this separation constant isn't anything tricky. We have homogeneous boundary conditions in theta. In theta, we have homogeneous species. Right, so they're both 0. Therefore, we want oscillatory solutions. Okay? And because we want oscillatory solutions, we're going to set a separation constant here to be positive. Because the positive separation constant will produce oscillatory solutions in sine and cosine, thanks to this differential equation. So we've also seen, we should have seen where I'm arrowing right now, we should have seen this equation multiple times before in circle problems and in the previous cylinder problem. So in step 2, solve the diffie-qs. We're going to solve for h first. Hopefully things will come to light as we chug along here. So the differential equation for h is 1 over h d squared, let's move this h to the other hand side, d squared h dz squared is equal to h times lambda. Okay? Remember that we need the values of lambda to be in such a way that we produce oscillatory solutions in Z. Star this. We need oscillatory solutions in Z. So therefore, the only way to force these oscillatory solutions with this differential equation that we have right now is to make the value of lambda negative. Okay? So we're going to make lambda a negative number. So therefore, the solution to this differential equation right here, if lambda is a negative number, right, is C1 sine oscillatory, right, square root of lambda times Z plus C2 cosine square root of lambda times Z. There should be negative right here. Yeah. And if we plug in the first boundary condition we're given, so h of 0 is equal to 0, I believe. Yeah, so the bottom is equal to 0. We get that C2 is going to be equal to 0. Then we have to take the first derivative of Z, of this function, and that gives us C1 square root of negative lambda cosine square root of negative lambda times Z. And then evaluating this first derivative at h gives us that C1 square root negative lambda times cosine of square root negative lambda h is also equal to 0. So now we have now we have to find the values for lambda. And given this periodicity condition right here, we know that square root of negative lambda times h is going to be equal to 2n minus 1 divided by 2. So that's the relationship for cosine. So lambda in this problem right here is going to be equal to 2n minus 1 over 2 divided by h times the negative. Okay? So like I have said earlier, we're forcing lambda to be a negative number. And the reason for this will soon come, I promise. So just take my word for this for now, that lambda is equal to this negative garbage stuff. Oh, that's squared, I did. And therefore, h of z is equal to c1 sine of 2n minus 1 over 2h times z. Great. As a side note, these boundary conditions that result in these type of weird eigenvalues are called Robin BCs. And they're also referred to as the third type of boundary condition. So actually not step, we're not even at step 3 yet. Let's solve for g of theta next. We need to continue solving for differential equations. The differential equation for g is as follows: d squared g d theta squared is equal to negative mu g. And since we know that we want oscillatory solutions, this is fine and dandy. So g of theta is equal to c3 sine of square root mu theta plus c4 cosine square root mu theta. Let's plug in the first boundary condition, which states that at 0 we're equal to 0, and that tells us that c4 is equal to 0. And the other boundary condition is at angle pi, we're also equal to 0, and this gives us the standard eigenvalue relationship. And this consequently tells us that mu is simply equal to m squared. Let's box that in green because that's important. Where m starts from 1 and goes on to infinity. And then if we evaluate, the differential equation for g, therefore, is just going to be equal to c3 sine m theta. And let's take a look at f of r now. Let's go back up here. So f of r looks like this. Is equal to mu. Yes, mu. Oh, I made a slight mistake. I forgot to account for this lambda right here. So what we're going to do is we're going to quickly shift it over, because that's how we do this. Plus lambda times r squared. And now we should be fine and dandy. My bad on that. All I did there was I forgot to account for that lambda. So plus lambda r squared is equal to, I believe, negative mu or mu. Okay. All right, so this is a slightly, this should seem familiar to Bessel's differential equation, but there's a slight tangent with it that we'll slowly talk about. So we have r squared, f, so I'm expanding the left-hand side of this equation, df dr, plus f times lambda r squared minus mu equals 0. Let's substitute the value for mu in, and that should be equal to m squared from what we just found in this semicircle problem above. So let's just copy and paste that. And let's also copy and paste down the value for lambda. Remember that lambda is equal to negative n pi. Oh wait, lambda's equal to a very big number. Let's copy and paste that very carefully. Lambda is here. Let's take this value. Negative r squared minus m squared is equal to 0. Alright, let's be very careful. So normally, what we could do, this is a tangent right here, so just follow along. Normally what we normally did for Bessel's differential equation is that we set this variable z, so the change of variables thing, let's call it zeta, and so we don't mix it up with z from earlier, and we would set this variable as 2n minus 1 over 2h times r. And then if we did the full change of variables, what we should get is zeta squared over d zeta squared plus zeta df d zeta plus f negative zeta squared r squared. Oh, it's negative zeta, sorry. Negative zeta squared minus m squared. Sorry. Oh, my bad. Okay, so we need to have a negative. We need to have a I there so that we can get rid of that. There we go. Positive. Yeah. Okay. So that we can appropriately substitute in I, and then it cancels it out. This should look like Bessel's differential equation to you. But this form of Bessel's differential equation is a little funky, to say the least, because it gives rise to these weird type of solutions that we don't normally see. Right? In fact, although it's J of M, it's of order, it's of the imaginary order is what I'm trying to say right here. So everything I'm doing right now is what we normally do, but then if we substitute in the value for Z, C5JM, we get these imaginaries. And blah, blah, blah. This is where the issue comes in, right? And this is where modified Bessel functions come in. Bessel functions are not defined for imaginary inputs. Okay? So this is why we can't go about this in a normal Bessel's differential equation way, right? We have to do a slightly different substitution as opposed to the one that makes us go into the imaginary plane. So instead of doing that substitution with zeta equal to I times whatever, let's do a different substitution with let's say S. So let S equal 2n minus 1 over 2h times r. Okay, so we're going to get s squared times d squared f over ds squared plus s df ds plus f over negative s squared minus m squared. So this looks like, this equation right here looks very similar to Bessel's differential equation, but it has a different name. It's called Bessel's modified diffeq. And the big reason for this is this negative sign right here. That negative sign changes a lot. So that forces Bessel's modified Bessel functions to appear, because the solution for this turns out to be something nice and simple. So f of s is equal to, I think it's C7, I of m s plus k of ms. All right, so normally we saw j and y, but now we have I and k. Now, let's take a look at what I and k look like. And this is the picture I had up in the beginning of this problem right here. So I is well behaved at 0. Is well behaved at 0, whereas k is not behaved at 0, i.e. undefined. Right, because the function for k here, which I'm going to trace in pink, is this thing right here, and function for I of I0 in blue here is just this function right here, right? So if you guys remember the boundedness condition, right, since we're inside the cylinder, boundedness condition, which I'll write for completeness here, boundedness condition is that at center of circle there is a singularity, and therefore we have to force the limit of r as r approaches 0 of our function u r theta z, absolute value of this has to be less than infinity, right? Because in a heat problem we can't have infinite heat at 0. A very important point I'm trying to stress in these type of problems, called the boundedness condition. Okay, so if we take the limit, actually let's plug in the value for s back in. So f of r is equal to c7 I of m times this crazy looking thing right here, 2n minus 1 times 2h plus c8 km of same thing. Here, the limit of f of r as r approaches 0 absolute value must be less than infinity. Okay? But the issue is that, remember that in the graph of k is poorly defined at 0. Therefore, C8 has to be forced to be equal to 0 to satisfy the boundary condition we gave above. So consequently, our function for f of r is going to look like C7 times Im times 2n minus 1 over 2h times r. So let's talk a little bit about the value for lambda now. Remember how I was telling you guys that lambda needed to be equal to a negative number, okay? So in a normal cylinder problem, when we say that lambda is a positive number, that implies that when we solve for the values of lambdas correspond to the zeros of the j function, for example. I remember explicitly from the last problem that we did, a cylinder problem, that the lambdas in that problem, lambda was equal to alpha mn squared, right? Where alpha mn corresponded to each of these zeros, right? So 1, 2, alpha 3, blah, 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 blah. Because those lambdas were corresponding to the zeros of the Bessel function. However, I and k do not have any zeros in the positive set of numbers, right? So if you just look at the x-axis right here, no zeros. Consequently, if we had positively defined lambdas, that would give us the implication that we have zeros along the x-axis. Positive, I'll write this out, positively defined, actually let's just say positive lambdas imply zeros on x-axis. Not true, right? Especially for modified, only for modified. Therefore, negative lambdas result from these type of problems because of the simple fact that there's a contradiction in saying that we have positive lambdas. Saying we have positive lambdas implies that we have zeros on the x-axis, which is definitely not true. So consequently, these negative lambdas arise as a fact of the contradiction that's implied with positive lambdas. So this should give the answer of why we use a negative lambda as opposed to positive. And this is, I think, the first problem where you guys are seeing negative lambdas arise, and it's a very weird type of problem for this sort of thing to arise. Please rewind the video if what I just said doesn't make any sense, because this is a very strange thing to think about. All right, so let's put everything back together now. So step 3, put everything together. Remember that we define u of r theta z to be equal to the product of f times g times h. So therefore, u of r theta z is going to be equal to whatever we take the products of. So let's take a quick look at what we called h here. So h of z is equal to this differential equation, this solution right here. Let's take a quick look at what the value for n is, and it should be equal to 0, 1 to infinity. And the quick reasoning for this is because let's quickly check what lambda can be equal to. Can lambda be equal to 0? Let's do that quick check right here. D squared d8 dz squared is equal to 0. The solution for this is going to be equal to some constant times z plus another constant. H of 0 is equal to 0. That's equal to b. Dh dz of 0 is equal to a. So therefore, h of z is equal to 0, and that's the trivial solution. So therefore, h cannot be equal to 0. And in order for this lambda to be equal to 0, the smallest eigenvalue would have to correspond to a value of n is equal to like 1/2, for example, but that's not possible because n is an integer. So we have to start at the smallest eigenvalue for Sturm-Liouville to satisfy Sturm-Liouville properties. So the smallest eigenvalue in the set corresponds to n equals 0, and then n can go from 0, 1 to infinity. Because at 0 we're not actually equal to 0, so we're good. So let n equal 0 there. So the summation is going to be n equals 0 to infinity, m equals 1 to infinity. We have a constant coefficient here, times I of m times 2n minus 1 over 2hr times, let's see what else we have here, sorry. So the g of theta term, which is sine m theta, and then the h of z term, which I'm just going to copy and paste down. Sine m theta plus this term right here. Great. So now we can solve for the coefficients. Solve for coefficients slash apply IC. So the initial condition we're given here is on the edge of this, on the lateral surface of this cylinder. And that's telling us that that's equal to beta theta z. So let's plug this in into our problem. And then we should get something nice and dandy. So this is at specific height. This is at some arbitrary z still. Right? And this should be an h. But we're evaluating at a radius a. Great. So consequently, if you guys have gotten good at orthogonality, this is an example of a 2D orthogonality problem. There's a lot of stuff here to be considering. So there's going to be a double integral from 0 to pi, and then from 0 to h. So since we're integrating over theta and z, of beta theta z times sine m theta times sine of 2n minus 1 over 2h z d theta dz over, so this is going to be a constant now because we're valuing at a specific radius. So I of m times 2n minus 1 over 2h a over the double integral again, h sine squared m theta sine squared 2n minus 1 over 2hz d theta dz. And that should be your constant coefficient. And then your general solution for this problem would be this. So these two together, the two blue boxes, would be your final answer to this problem. So this is the first type of modified Bessel problem that you guys will probably encounter. And this would probably be the first type of problem where you guys will see a negative eigenvalue. But I would say this is a very, this would be a more difficult type of problem that I would expect to might see on an exam. But yes, if you guys are able to do this problem, you should be able to do most cylinder problems, and this should be a very simple facet of Laplacian equation problems that you guys should be able to do. But I hope this video helped you guys. Please let me know if you guys have any comments, questions, or concerns in the comment section below, and good luck with your studies.